Hey, it's Matt from Cast Labs, and today we're going to be looking into tire inserts and how they affect the ride. So the way this came up was CushCore hit me up and sent me some free stuff. They sent me some inserts and a few sets of tires, probably thinking I'm good for marketing. Anyways, it fooled me because here we are. But I actually thought it'd be really cool to look into. You know, I traditionally think of tire inserts as just protecting us from catastrophic wheel failure. But now I'm wondering, does it significantly affect the way that the bike rides? You're adding some unsprung mass, you're adding some rotational inertia to the wheels. So maybe it's going to ride a little worse, but also we're able to drop the pressure significantly. So maybe that confers some benefits to the ride. So that's what we're going to look into today. A stock setup with no inserts, a setup with inserts at the same pressure, and a setup with inserts at a lower pressure. So we're going to see if those feel any different on the bike, and also look at a couple metrics, one being traction, which we've talked about, but two, also vibration isolation. So seeing if the insert with low pressure is able to isolate the rider from harsh vibration better than maybe the stock setup. So we'll explain those metrics, then we'll go into our field testing, which was partly done by me, and then I also had my buddy and local legend Nicky D do some riding for that, which was awesome, and then we'll break down the results and see what we learned. Okay, so let's talk a bit more about this idea of vibration. So in a lot of industries like automotive and heavy equipment and power tools, they've done a lot of work in quantifying what vibrations or accelerations we find really uncomfortable or harmful. And there's actually an ISO standard that kind of lays out this guideline of saying, hey, these vibrations we really don't like and are uncomfortable or unsafe for us, and we should be minimizing vibrations in that kind of range. So when you think about riding your bike, your hands and your feet are subject to all sorts of accelerations. You're getting shaken up by the trail. And the idea here is that we want to minimize the vibrations that are getting to the rider that we find really uncomfortable. And so I'm going to try to explain how this ISO standard lays out computing this kind of uncomfortable vibration score. So we can start here with our accelerations in X, Y, and Z. So you can think, this is how we're getting shaken up vertically, laterally, and fore aft. And basically what we do is, this is acceleration with respect to time. What we do is we actually change this for each of the axes into the frequency domain. And all this is it's how many times per second something's happening. So really low frequency could be, pump and rollers. Higher frequency is like braking bump chatter. And there's, even higher frequencies that maybe are really hard to perceive in terms of a trail event, but they're happening nonetheless. So now we can kind of see, we have lots of accelerations like at this frequency, we have a lot of accelerations at this frequency, and it kind of dies off. This is just a random example. So once we have all of our accelerations in the frequency domain, we can now apply this ISO weighting. So this ISO weighting just says, hey, we really dislike frequencies from like 10 to 40 hertz. By like 100 hertz, it's not so bad. By like 200 hertz, it's negligible. And so we basically slap on this weighting curve to our acceleration in the frequency domain, and then we convert our weighted accelerations in the frequency domain back into the time domain. So now we have these accelerations weighted such that it penalizes the accelerations that are in those kind of uncomfortable frequency ranges, and it maybe doesn't give so much weight to the accelerations that are, outside of those frequency ranges, like here. And once we do that, then we compute the RMS of these values. So we kind of combine all these to get a magnitude, compute the RMS, and then we can get out kind of a single value. So if we get some frequency, weighted, we might call this like a vibration score. When you're riding down the trail, for one setup, like your shock in your normal setting, it might be this. And then maybe you lock out your shock and do the same run. You're probably going to be subjected to more uncomfortable vibration than your shock like set up properly. So that's kind of the basic idea behind this ISO weighted acceleration or like vibration score. Beyond being super common in other industries, I think it's actually used semi-often in our industry. One example is that SRAM used this kind of like frequency domain analysis of acceleration data to evaluate and kind of benchmark their Buttercup technology. There's an article about it online that's kind of neat. And then also there's a ton of different like academic research and papers on vibration isolation with bikes, varying tires, and other stuff like that. But yeah, so we're gonna take a stab at doing this today. Okay, to hopefully make the frequency domain stuff make a little more sense, I have a cool little example for you guys. So I went out to my local trail behind the house the other day and recorded 5 short sections of trail, about 15 seconds each, with my stock suspension setup. And then I did 5 runs of the same little section of trail with my fork and my shock locked out. And so we're gonna take a look at the frequency domain of these kind of 2 settings and see if we see any noticeable differences. So first we're looking at our X, Y, and Z acceleration from one of these sample runs just in the time domain. So you'll see we're getting started here on the left, and then as we get to like 5, 6, 7 seconds, we're speeding up, and we're now getting subjected to some, pretty big accelerations as you would expect riding trail. But this is just what you would expect acceleration data to look like while we're riding our bike. So now when we convert it into the frequency domain, we're looking at accelerations on the y-axis, sort of. We're kind of looking at like the power of the signal, but basically just think like the higher the value, the more acceleration we're seeing. And then on the x-axis, we're looking at frequency, we're looking at hertz. And so we have an example here with one of the stock runs in orange and one of the locked out runs in green, and you'll see a very clear difference. Wow, we have so much acceleration happening around, 16 to 20 hertz, which is actually, according to that ISO standard, what we really dislike. It's the vibration that feels really uncomfortable. And so hopefully this explains or shows, hey, when we're locked out, we're seeing vibrations in this area that are way higher than what we see on our stock open setting, and that's what's making things feel really uncomfortable. So hopefully that's kind of a simple example that makes the frequency domain stuff make sense. I just want to go over traction quickly. I covered it in depth in a previous video, so you should watch that, but there's a few things I want to note. So as an example here, I had a test run that I did on a local trail behind my house. The orange is your front wheel speed and the green is your rear wheel speed. And I measure these with a bunch of magnets on the wheels. And basically traction loss time is the amount of time we spend with the rear wheel spinning at a certain percentage below the front wheel. We set some tolerance because, the wheels aren't always going to be exactly the same speed, but when it gets drastic enough, then we capture that as traction loss. And traction loss intensity is just how much slower the rear wheel is spinning. So if your rear wheel is like locked out, it's 100% traction loss intensity. A couple buddies and I have talked about whether this algorithm captures just longitudinal slip and also if it just captures slip while we're on the brakes. So I went out to do this test to validate if the algorithm's picking up, out of plane traction where I'm kind of slapping into corners and stuff like that. So what I did on this run is I hit a button that was on my handlebars every time I noticed traction loss. And so all these little red flags are the button presses, and all the green spikes are when my algorithm picks up traction loss. So you'll actually see on this trail with a bunch of cornering and a bunch of kind of varied terrain, the algorithm did a really good job at picking up almost all of the traction loss events. And this includes the ones that were out of plane and happening while I wasn't even on the brakes. So while it's not perfect, I missed a couple of these events here, and I suspect maybe this is when I'm going through kind of flat corners and both my front and my rear wheel are kind of skipping over the terrain laterally. So it's not going to be able to pick up events like that, and I'm sure it's going to miss a lot of other stuff. But despite these limitations, I think it's a decent proxy for measuring traction loss, especially as kind of a quick and dirty algorithm. We got Nicky D's bike all instrumented here. The most important things here are wheel speed sensors. I've updated my mounts with this little 3D printed mount that kind of captures the magnet on 2 spokes so the magnets don't rotate, which would make it hard for the little reed switch to pick up. And then we've got rear wheel speed here. We've got the data logger with accelerometer, gyroscope, and magnetometer inside. We'll mostly be using the accelerometer in that, and then we also have an external accelerometer mounted at the bars, and this is going to be kind of a proxy for picking up vibration at the touch point at the handlebars. While I show you guys a bit of the track preview here of Nicky riding dangerously fast on jugs, I'll explain a bit of our test setup. So we tested 3 setups. The first one is stock, which is Nicky's normal riding setup. It has no CushCore inserts, 27 psi in the rear, and 24 psi in the front. Then we tested stock pressure with CushCore, abbreviated to SPC, which has inserts and the same pressure he normally runs. The final test setup is low pressure CushCore, abbreviated LPC, which has inserts, but also a 5 PSI drop in pressure front and rear. I think we did 15 runs, so 5 of each. The track was pretty dry. It's got a lot of varied terrain, some steep stuff, some chunky stuff, lots of corners. So I figured it would be a good track to encapsulate differences in traction and also in kind of vibration or bump isolation from those rough sections. Okay, so I'll shut up and let Nicky's riding do the talking for a bit, then we'll get some of his subjective feedback and then go into quantitative results. First lap with low pressure CushCore, how did it feel?
I did feel that when you were really like leaning over through the corners, then that's when the biggest like difference you can tell. The best way to describe it, just more planted in those kind of like loose corners, and even just off the top, like jumping through all the holes. Less feedback a little bit, like with your hands and feet.
We are going with high pressure now. Well, the same pressure we had with the stock setting with no CushCore. We're going up. Oh, we gotta drop the pressure a bit. We're going back up to 27, 24, and we're gonna see what Nicky thinks of that. We have some suspicions.
Yeah, so just finished up CushCore with the high PSI again, starting off like 24, 27, I believe.
That's right.
Yeah, definitely like right away once you're dropping in on the trail, like I mentioned last time, that like connection to the ground and just like plush planted feel. Basically all that was like out the window.
Whoa, really?
Yeah.
Like in the top, like the high speed,
like the first
chunky.
30 seconds of the trail is very chunky, high speed braking bumps, and prior where you really felt the tire connected to the ground and like this planted feel was basically this really just harsh feeling. Like the tires, it felt like you were running, you know, 30, 35 PSI maybe in a regular tire almost, is like what I felt like. I don't know, I felt like I wasn't as confident.
From CushCore high pressure back to low pressure, what's the verdict?
Noticeable change.
Cool.
Pretty insane. Definitely got back to that just kind of planted feel of the bike, where it wasn't like pinging just off of the tree roots and braking bumps and stuff. You could really like kind of commit a lot more, and I was almost trying to like get off the brakes a bit more, like coming into the corners.
Okay, cool.
Like do a lot of braking before and then just carry speed through.
So 5 PSI, big difference.
Yeah,
Sick.
Insane. Definitely like make or break of the ride. Sick. Like I would not ride that.
What you were
like
just on before,
5
right?
PSI higher.
To your regular pressure, no CushCore, how was it after the CushCore lap?
Felt closer to the same higher PSI with the CushCore.
Oh, really? Okay.
Kind of made me second guessing, kind of messing with tire pressure a little bit more.
Yeah.
But yeah, I guess the biggest thing, which I was surprised by, is just that like planted feel and like the feedback almost, where I wasn't really expecting that as much to be like the main point.
Okay, before we jump into the results from the testing with Nicky, I want to quickly show the results from the test that I did on my own. And in this test, I did 4 runs with the stock setting on jugs, and then 4 runs with CushCore installed, and a 5 PSI drop in both tires. So for my analysis, I really want to focus on building links between qualitative rider feedback and our quantitative results. So in my feedback notes after each lap, there were a couple times on the low pressure runs where I wrote that I didn't hear a single skid or break of traction on the whole run. You know, this is pretty rare for jugs, especially in the summer. And we kind of see this being borne out, that I felt a lot better traction on the low pressure settings because, you know, look at the times here. They're pretty low magnitude overall on average, but there is quite a big difference. You know, we have less than half of the amount of time spent slipping when we're on the low pressure setup. Another interesting thing is I didn't feel basically any difference in terms of vibration. Like I didn't feel more rattled around on one setup versus the other, which I was a bit surprised at. And this is kind of borne out in the data as well. The vibration scores are basically identical. It's kind of interesting to see that our quantitative results are really linking up with what we're feeling on the bike. Kind of means that we're on the right track with what we're measuring. Okay, so let's dive into the field test results from the testing with Nicky. You'll see here I put together some of his feedback notes. And this should give us an idea or some clues into what we might expect to see differently quantitatively in the data based on what he's actually feeling on the bike. So we may expect that we'll have differences in traction because he says he feels a lot better in the corners with that low pressure setup. He feels a lot more confident to really push and keep leaning into corners more than the other two setups. The biggest difference for him was actually the vibration stuff. He felt like he was being rattled around a lot, especially with the stock pressure with CushCore installed. Okay, so now looking at the weighted vibration score filtered for that top 30 to 45 seconds of trail where Nicky was feeling it the most, we actually do see that the low pressure CushCore setup had the lowest vibration score compared to stock and the stock PSI CushCore. And it's interesting, we see at the accelerometer on the down tube, the same kind of trend as the accelerometer on the handlebars. So the down tube is probably a decent proxy for the vibrations that the rider's feeling at the touch points, though our magnitudes were higher in terms of the acceleration at the handlebars. It's not a huge difference, 4 or 5%, but it's potentially big enough to be what Nicky was actually feeling out there. Doing a little bit of a deeper dive here, I want to look at the frequency domain results from a couple of runs as an example. So in orange, we have the low pressure CushCore, and in green, we have the stock pressure CushCore. A couple notes, you'll see that these PSDs die off really quickly after 50 hertz. Part of this is because the weighting function from the ISO standard, discounts all the stuff happening up here pretty quickly. The other thing that's going on is that my accelerometers internally and the external ones have hardware filters, and one of them's a digital filter at about 250 hertz. So we're not even looking beyond that. Anyways, let's zoom in on the interesting stuff. Remember, low pressure settings in orange, and high pressure, or the stock pressure CushCore, is in green. And so it's a lot more subtle than when you fully lock out your suspension, obviously, but you'll see in these areas, particularly where we feel it the worst, kind of from like 18 to 20, I guess it's this whole kind of region from like 15 to 30, but you'll see that we do have some higher peaks here on our green stock pressure CushCore. And then we also have this other peak around 20 that's interesting. And then in these lower frequency zones, maybe around 15, we have much more signal content here, which is interesting. And a little more kind of accentuated signals down in the low frequency zone. So you'll see, even over an entire run, there's enough of a difference here that I definitely think that this is what Nicky could be feeling. And the interesting thing with these two runs is these are back-to-back runs. So this low pressure run was run 9, and the stock pressure run where we upped the pressure was run 10. And he did feel a big difference between these runs, which we're kind of seeing in these results, which I think is actually really, really cool. Okay, so now let's look at traction. We see here in traction loss time, the setup that has the most traction loss is the stock pressure CushCore, a little over 3 seconds a run. It also has the highest traction loss intensity. This is then followed by the low pressure CushCore, and then followed by stock. It's interesting to see stock have the lowest traction loss time, because we would expect the low pressure CushCore to be based on Nicky's subjective feedback, because he said he felt like he had the best traction with the low pressure. He could really push into and lean into corners and trust his tires a lot more in corners. But then upon thinking about this more, I thought, Nicky did say that he's coming in a lot quicker. He can kind of let off the brakes and push into corners a lot faster with the low pressure setup. And so what I did here was bin traction loss time based on bike speed down low, and you see that Nicky's actually losing traction on average at these higher speeds with the low pressure CushCore setup. So this could imply that, hey, he's feeling more confident, therefore he's pushing it a little harder, and he's losing traction on average in higher speed zones. One more thing I wanted to show was the run level plots of wheel speed and traction loss. You'll see that between different test setups, which I'll toggle between on the plots here, Nicky's losing traction in different places. This is kind of implying, hey, yeah, that confidence he's feeling, or the difference he feels between setups, forces him to kind of ride to the bike setup or ride differently based on what he's on. All right, so let's wrap this up. First thing is I just want to shout out CushCore again for sending the free stuff, because this ended up being pretty fun and informative. I also want to shout out Onyx, who sent a couple wheel sets with their instant engagement hubs. I was interested in getting these to do a deeper dive into pedal kickback, which I'm kind of working on in the background now, so expect to see more research on that front soon. But for this test, just having 2 wheel sets kept us from having to swap tire inserts and tires between runs. Instead, we just swapped wheel sets, which was nice. So thank you, Onyx, and more pedal kickback research to come. So big takeaways from this test: tire inserts are definitely more than just rim and wheel protection. It definitely affects the way the bike rides. Across setups, we saw differences in traction performance and vibration isolation. And so one of the big takeaways here is if you're running tire inserts, you may want to consider dropping your pressure a bit, because otherwise you may be having a bike that's riding worse than it normally would, and also you're losing those potential benefits of having that low pressure, maybe isolating you from harsh vibration or bumps, and also giving you a little better traction. Of course, we didn't test climbing, and this is something that riders should consider. You're adding more unsprung mass, you're adding more rotational inertia, and if you drop your pressure, you're also having more rolling resistance for climbing. So that's kind of a trade-off that the rider needs to consider. Another cool thing was how the same setup change manifested differently across different riders in terms of performance. So I felt subjectively and quantitatively like I got better traction, but really didn't feel any differences in terms of vibration isolation, whereas Nicky felt the biggest difference for him was a low pressure setup kind of muting the trail and taking out that harshness. So that's maybe a tough thing for bike companies because every rider is super different and unique and everything manifests differently, but it's cool to see that bear out in the data and in our feedback. Lastly, this testing reminded me of that super important and honestly impossible to quantify concept of rider confidence. This is really the biggest thing at the end of the day, like how does the rider feel? And the bike industry, honestly modernity in general, has kind of a strong bias towards empirical methods and like trusting the data or the science or whatever. And we should be sure to use these like quantitative methods as tools to achieve the ends of rider feel and rider perception being awesome. The tools and the data is not an ends in itself. So we should remember that. From this testing, our quantitative results showed that the low pressure setup, was a little bit better in a few areas, but Nicky's feeling of confidence and being super stoked on the low pressure setting, maybe is impossible to quantify, but probably the most important thing. This talk about rider confidence reminded me of a passage from the introduction of my copy of the Iliad, which talks about morale in soldiers, which is kind of the analog to confidence in riders. So I'll read that passage to finish up. It's kind of cool. This is not a modern way of looking at battle, but it is a striking way of expressing one of the mysteries of combat, the unpredictable currents of aggressive courage or faltering panic which sweep through armies, the mysterious factor known as morale. It is not a factor that can be fed into the computer, though that expert on the subject, Napoleon, said it was 3 times as important as material. And everyone who has been in battle knows how intangible and unpredictable it is, how hard-pressed, outgunned men can suddenly take the offensive and turn the tables, how victorious advancing units can develop an uneasiness about their flanks that can turn into panic. And in fact, battle is always unpredictable. I thought that was kind of cool and reminded me of, Nicky's confidence while riding. So that's all for today. Let me know what you guys think, if you have questions or critiques, and what you want to see me research next.